So in the last video, we saw that Maxwell's equations led to the discovery or the understanding of electromagnetic waves. By electromagnetic waves, we mean a wave that has an electric field portion and a magnetic field portion. If I write these equations similar to what we did with our traveling waves and similar to how I did in the last video, writing them both as a function of x and t implies our wave is traveling specifically in the x direction, and then the value of the electric field and magnetic field depend upon x, meaning where from the source we're talking about, and t, when are we talking about it. We learned that the electric field direction, is perpendicular to the magnetic field direction. The electric field and magnetic field are in phase. That means they are zero at the same time. If the electric field is zero, then so is the magnetic field, and vice versa. If we look at a moment in time where the electric field is maximum, then so is the magnetic field. We also learned that the maximum value of the electric field divided by the maximum value of the magnetic field, that ratio is equal to the speed of light. Now, one equation to talk about first here, this equation is called the Poynting vector. And yes, this is how it is spelled. The equation looks like this. The Poynting vector is defined as, if you recall, those three lines mean not only is it equal to, but it is always also a definition. The Poynting vector is equal to 1 over mu naught, the constant we saw a lot with magnetism, times this quantity of the electric field crossed with the magnetic field. I like to think Poynting vector as in S points in the direction the wave travels. That means if you use your right-hand rule and figure out the direction of E cross B, it gives you the direction of S, which is the direction the wave travels in. Now, this equation does not give you the speed of the wave. This equation describes the energy flow. It describes the energy flow of the wave. So we can say, because E and B are perpendicular, we can say that this energy flow is simply E times B over mu naught. And by energy flow, we do mean watts per meter squared. If you recall, watts per meter squared were the units of intensity. But this equation, as it is written, if we plug in E and B from up here, well, E and B both change, and they have different values based off of where from the source. So X up here is the distance from the source, the oscillating charges that are creating this electromagnetic wave. And then t is the time we're looking at it. So what moment in time are we referring to? Since E and B are varying both in where we're talking about and what time, this equation gives us an instantaneous, is that how you spell it? An instantaneous intensity. It's changing because both E and B are dependent on X and T. X meaning where from the source, and T meaning when we're talking about. So for example, if we think up in this list of things we know about our electric and magnetic field portions, E and B are in phase. If we think about a sinusoidal function, there's moments in time where both of them are zero. If the electric field and magnetic field are both zero, then our equation down here for the pointing vector tells us that we're talking about an intensity of zero at that moment in time. Which, when we talk about intensities of waves, we're talking about an average intensity. So really, what we want to talk about is an average intensity. This will be listed as an S average. It is also showing I for intensity. And if you recall back to waves when we talked about them before, this is power. So the power of the source emitting the wave divided by area, the area the wave itself spreads over. But we need to first talk about how to get this equation up here to represent an average value. So let's graph the electric field. I'm going to say there's no phase shift. So I have just a nice perfect sine function. This would be true. This could be X or time. It doesn't matter. If you recall, we have snapshot graphs and history graphs. It doesn't really matter which one I am looking at the moment. So we know this electric field depends upon both position, so how far from the source I want to know its value, and at what time. I'm leaving off phi naught since I chose to draw it as a sine function, then there is no phase shift. We know the average value of E is 0. The average value of a sine function is 0. And so if we want to talk about average intensity, well, the average intensity is not 0. An electromagnetic wave, a great example of an electromagnetic wave is light. If I turn on a light switch and my light bulb turns on, I have light that can help me read, help me see. So that is most definitely not an average intensity of 0. Average intensity of 0 would imply nothing, no light. So that's not what we end up seeing. So what we do here, because E and B are always related, it turns out we can rewrite this pointing vector equation in terms of just E or just B. So if you recall, speed of light was E naught over B naught. So if I wanted to plug in for E, I would end up with a B squared. Or if I plugged in for B, in my this intensity or pointing vector equation, I'd end up with an E squared. So what I'm going to do is let's look at what happens to our function if we square it. Well, if we square it, all of these negative portions go positive, right? Square root of a negative number is a positive number. So now we have our function squared. The average value of a sine function squared is not 0. I don't expect you to know what it is either, but I'm going to tell you. So this squared function is still changing. It's still a function of x and t. But if we want to think about what the average value is now, the average value of a sine squared value is 1/2. So we have this electric field. The average value of E squared is 1/2 of E naught squared. If I take the square root of both sides, we call this an ERMS. RMS stands for root mean square. And it explains what we just did. We squared the electric field. Then we took the mean or average value. That's where we got the 1/2. And then we took the square root. This gives me the average value of the E squared function. We could go through the same process using the magnetic field, because the magnetic field is also a sine function. If we went through the same process with the magnetic field, we find that the BRMS, standing for root mean square, is equal to B naught over the square root of 2. Where this goes is if we come back up to our pointing vector and we want an average intensity, we need to use RMS values. ERMS times BRMS over mu naught would give us an average intensity, which means it would equal power divided by area. But this relationship of C equaling E naught over B naught also equals ERMS over BRMS. If I solve these RMS equations in the bottom for the maximum values, E naught and B naught, and plug them in, the square root of 2 part would cancel. What that means, let's pull this down here a little bit. So average intensity this S average can be written as the ERMS BRMS over B. But because C is equal to ERMS over BRMS, ERMS would be C times BRMS. If I wanted to plug that in, so E would be C, oh, I don't know why I have a C on the bottom. That's mu naught, sorry. So C times BRMS for E So I could write this average intensity in terms of just this RMS value of B. Or I can plug in BRMS is equal to the maximum B over the square root of 2. I can plug that in. And this would become C B naught squared over 2 mu naught. So that's one way to write the average intensity. But we could have said BRMS is ERMS over C. If I come in and plug that in instead, BRMS, then my S average can be written in terms of just the electric field. And similarly, we know the RMS electric field is the maximum value over the square root of 2. We could write this average intensity in terms of just the electric field. Because the electric field and magnetic field are always related, it is totally applicable to write this average intensity in terms of either one. In the test notes, you're going to see or at least currently, as of the making of this video, not that the physics changes, but the way we could potentially write the test notes out later if we modify them. They also change it to be in terms of epsilon naught. So this is what you see in the test notes. I for intensity. The heading above these equations, or this line of equations, says intensity. I find this can be a little confusing since we've been talking current as well. So I tend to use S average for the most part, so I remember I'm talking about intensity and not current. But intensity I, of course, works just fine. Now, we want to keep in mind that this represents power of the source divided by the area. So power of the source, area the wave spreads over. You'll see in the test notes that I is equal to P source over 4 pi r squared. That's an R. And next to this says radially emitted. That would be like a light bulb. A light bulb, if I plug a light bulb into my lamp, the light is emitted in all directions. Now, granted, a little bit of the light is blocked by the base, but for all intents and purposes, that's what we would mean by radially emitted. What that ultimately means is if I'm over here, a distance of r from the light bulb, or up here, a distance of r, or over here, a distance of r, the intensity, the brightness would be the same, that same distance r from the light bulb. That's what we mean by radially emitted. The bulb is the center of the circle, so if I go the same distance in any direction, minus of course the base, then the intensity I observe would be the same. So that is what that represents. If we have something like a laser pointer, though, a laser pointer, you don't get that radially emitted. You shine the little laser light on a board or paper, all you see is a little circle. The circle of light. The intensity would still be the power of the source over an area, but it would be the area of just that circle of light. The area that the light itself is covering. So we'll do a few examples with intensity, and then we'll move on and talk about radiation pressure as well.